Our first presentation is from Greg Ivey. Greg's going to be presenting on the physical oceanography side of things for the Kimberley and the work he has done in that sort of bay domain that Matt was talking about. Greg.
Okay, good afternoon. So I'm going to talk about the physical oceanographic processes, and as Matt nicely summarized for you, the range of modeling. So where does this project fit in? So we're talking about this project down here. So we're focusing on the hydrodynamic or the physical oceanographic processes, and we're also interested in scales going from order of 100 meters out to order tens of kilometers offshore. And the sort of motivation for this modeling project is to answer some fundamental questions along what are the nature of the exchange or circulation and mixing characteristics in these obviously complex coastal environments that exist up in the Kimberley, and to ask, using those tools, to ask some very specific questions regarding how long do things like water masses, nutrients, and potential pollutants move through this system, and how does that vary seasonally as we go from the very dry season to the very wet season. So those are the general motivators for this kind of approach. Couple of things to point out here, as Matt indicated, the scale over which the modeling is to be done is this bay scale centered around Collier Bay, which, as you can see from the depth chart, there's a considerable variation in water depth from 10 to about 50 meters as you move through this system, as they move offshore and offshore, and also because of the complex reef systems throughout the region. The model, the way it's set up, is that it basically incorporates a description of this region over the depth. It's three-dimensional, it evolves in time, and it needs to be forced with the physical forcing variables that are driving the flow. And those are basically, we set up a model grid to describe the region. So we're talking about resolution of order a few hundred, 500, 600 meters. There's a sort of scale in the horizontal, multiple layers of meters in the vertical. It's forced by the physical forcing variables, the wind and the rain that varies on a daily basis, for example. Heating, as we go into the strong summer season, obviously the water column is going to get a lot hotter than it is in the winter months, for example. We also put freshwater inputs estimated from some other projects within WAMSI flowing into this system during the wet season in response to the aperiodic storm system passing through the region. So the thing to point out also is that on talking about modeling, one of the attributes of this modeling project is to try and evaluate the performance of the model against field observations. Field observations come from ship-based observations using cruisers with Ames's Ivey Salinity during the period, but also 3 moorings were deployed. These little purple triangles here are what we call the outer shelf, the mid shelf, and the inner shelf, the outer bay, mid bay, and the inner bay region as well. So these are moorings placed at those fixed locations, recording through the water column properties, which we can, at those 3 locations, evaluate measured reality against model performance, as an example. So there's an example of the sort of validation when you get the model and you run it. So these are field measurements were done during the period starting in 13 through to late 15. So this is a period during the early period, during January 2004, centered around there. So these are the black lines are obviously the model performance, in this case of free surface elevation. That is the free surface movement of the tide. Just to remind you that if you look at any one of these, so if you look at this period here, the free surface is moving from a minimum of 5 to +5. So the excursion of the water surface vertically in water column that's only literally tens of meters thick is going as an excursion of 10 meters plus or minus 5 meters. So there's a macro tidal region, very strong elevations in the vertical. And also it's not constant, of course. It varies during this, depends. Primary forcing agents are the moon and the sun causing the movement of the free surface. And those are not exactly in phase, which causes this basic modulation you can see where there's a maximum during spring tide periods, a minimum during neap tide periods, and then the excursion gets very large again. So typically over like a 14.8-day cycle. So that's the basic characteristics of the tidal forcing. Tide utterly dominates what happens in the region. Wind, etc., is much smaller effect compared to the tide. Going back to Matt's comment about models and data, you would think, so the purple is actually the field measurements, the mooring, and you think of this central one here, you think, well, it looks in phase, but you'll notice that the model is predicting twice what the actual free surface excursions measured from that instrument. Turned out the instrument was wrong. It has a problem with the pressure transducer, which is why the other two look remarkably perfect, and this one looks strange. And you can see that when you look at the same instrument. When you look at the velocities, the instrument's measuring velocity through the water column. So these are measurements of velocity at these three locations, and you can see in the outer bay, the inner bay, and the mid bay, there's a remarkable agreement between the magnitude as well as the direction of the measured and model currents. It's not the same everywhere, but you can see that this is also a reminder at this location, instantaneous velocities, depth average, get very large, of order a meter per second or more. But they're varying strongly in direction as they move through the system. You can look at other aspects of the comparison between model performance or model prediction and measurements. In this case, we're looking at temperature. And so these are now time series over a period of time covering from August through to October the following year, so almost a yearly cycle. Inner mooring refers to the innermost bay mooring, the one closest to shore in this particular example. Again, a comparison, you can see that over the season there is, of course, from both model and measurement, considerable variation in temperatures, water temperatures at both the bottom and the top get extremely high, well in excess of 30 degrees, cooling to something like around about 25 in the winter. And you can see for most of the year, because of the intensity of these strong tidal flows, the water column is very strongly mixed. So there's very small variations in surface temperature to bottom temperature, which is why the two systems look very similar. But you can see not just velocities and free surface elevations, but also a quantity like temperature. The model is performing extremely well in reproducing the measurements made. In this case, just from the moorings, and this is just 3 points to measure, but also the aperiodic cruises we made with the ships. You can also look at spatial variations of these properties as well. That's temperature. Salinity, obviously with the strong inflows that occur during the storm systems that can occur during the wet season, we get periodic pulses of freshwater input coming in from the coastal region, from the coast itself into the coastal waters, which is going to cause a local reduction in salinity compared to the offshore salinities of order 35 PSS, as shown here. So indeed, during the wet seasons, you can see that, in fact, again, in a mooring, again, same situation, salinities measured at top and the bottom. You can see this drop in salinities where the salinities are dropping of order a few PSS or parts per thousand, if you want to think of it that way, during the dilution, if you like, that's occurring during the wet season and the resultant freshwater input. So, and the upper picture up here is an example from field observations where the ship is actually making transects offshore, showing you this. There are slight variations in the vertical, but in general, the variation of properties in this system associated with things like particularly salinity is there's an offshore variation as you go to the relatively high salinity water offshore to the relatively fresh water that's occurring right at the coast, diluted by the freshwater input from the river systems themselves or the catchments themselves. So from those sorts of tests, you can actually get a sense of how the system operates, and then you can use with some confidence based on those comparisons of individual moorings and or with ship-based observations, you can start to look at the model performance on the scale of the model which is running, which is this whole Collier Bay scale here. And this is just a reminder of the complexity of the system here. So these are tidally average currents, and so what we call, you can think of them as measured at a fixed point. The model is physically set up to replicate the topography. And so it's predicting measurements of currents at fixed points throughout the system. And so the basic idea, as you can see in the central part of this system here, Montgomery Reef is the dominant reef system in the central portion of this region. And over this region, from this, the vectors here are indicating the overall directions of the circulation suggested by integrating together the model output over this period of time. And the range of residual velocities, that is the net velocity averaged over the tidal cycle. Tidal cycle is basically around 12.4 hours, and if you average velocities over those cycles, it's not like a water parcel that's sitting here will go for 6 hours one way and the next 6 hours returns to initial spot. It actually does move. There is residual motion, and that's really what's kind of shown by this diagram here. So there's net transport, if you like, through the system. It's not a simple oscillatory system where everything returns to its initial state. And that's key towards understanding such concepts as how does this system flush, how does the system move, how do pollutants or nutrients move through this system. So the residual velocities vary very dramatically from this is the thing to measure is the range of scales from millimeter per second to meters per second. So there are huge variations as I move horizontally through the system as two things vary. Firstly, the water depth varies, and also the local strength of the tidal motions associated with the forcing as we move through there. So another way to look at it, and hopefully this little model will run. So one way to visualize this complex system is to see the flow of particles, and that's really the point of this, is now we call moving to a moving frame of reference or a particle system. So if you watch the clock up here, we're talking about each oscillation is around a tidal period of 12 hours. And you can see that across the line we've defined as the boundary of the bay, there is huge horizontal excursions of kilometers every tidal cycle, as in this case, fluid particles marked by these float particles, which are changing color as they move in and out through the system, make dramatic excursions in and out. It's not the same. You can see there's preferred paths in this system. You can see these particles, and also it's not simply returning. You'll notice these particles starting in here have moved out, they're staying out. So in other words, you get the suggestion that there's some sort of flow in this direction averaged over many days or cycles. You can see on short term, there is very strong oscillations in and out. Montgomery Reef sits in the center here, which is why it tends to be a region with low average velocities. If you like, the water is extremely shallow over that region. But as you vary in depth, as you move through the system, the intensity of the flow and hence the net residual motion and these particle motions changes with time. So okay. So that's the sort of hopefully that conveys to you the complex and dynamical nature of the system, how much it varies, not during just 12 hours over a tidal cycle, but how much the whole system varies as I move through the system. If you look at the model, typical model velocities averaged over the depth can be as large as 3 meters per second. You can see this from the ship. The velocities are so large, you get small whirlpools with depressions of the free surface associated with this. Not a typical oceanographic observation, I can tell you. You can summarize these ideas in calculating quantities like how long does particles retain their coherency or in this system, how long does the system flush. And here's an example of integrating that knowledge from those particle motions. You can show that from these sorts of analyses that the system does flush, but on quite long timescales. It's not one tidal cycle of half a day, but more like tens of days. So depending on where you are, offshore, closer to the open ocean, it flushes faster, whereas if we go into the inshore regions here, flushing times during the dry season are as long as 3 months, so they're quite long time frames. When rainfall does occur, it's not of course constant. In this case, during this calendar year we're working at, the little red line here indicates the start of measuring inflow in the system. The peak occurred in February in terms of peak flow. This is the catchment input in terms of flow rate Q, and essentially disappeared by late April here. You can use that information to calculate now basin or bay-wide flushing times, and that's what this one shows here. If you take the whole of the system, you can see the average flushing time for this system is around about 2 months, 60 days. During this period here, precedes in fact when the maximum in the inflow occurs, because most of the stuff is still driven by the tidal motion itself. Close to the coast itself in Walcott Inlet itself, the flow is very low, the flushing is very low, but as you go into the dry season, of course, there's no freshwater input, so there's very little flushing of the really inshore coastal regions and the bayments in the estuary. And to remind you, what you've seen is where this model fits in the hierarchy, and it's a tool that can be used for quantitative prediction of transport, of pollutants, fate and transport. can be extended to larger scales and linked to some of the other concepts and projects that are going on in here. Thank you for your attention.